Hey everyone, this is John. In today's recitation, we'll be talking about advanced Bessel function questions, more Bessel function questions that you might typically see in future exams and are applicable to future shapes such as cylinders. And then we'll talk about modified Bessel functions, which are a little bit sort of a different type of Bessel function, but are pretty straightforward once you get the hang of it, I think. But they do introduce some strange concepts that we'll take a look at, especially for the lambda equals 0 case. So this first problem that we'll be talking about or doing is from fall 2019 and Chingli Chai. You can find this exam on my website. This is from midterm 2 specifically, and this was the class that I TA'd before last semester. So in this question, we're told that we have a vibrating circular membrane, so let's highlight this, and we know that we are multidimensional, so we have x, y, and t. So noting this, we're probably going to have two separation constants down the road. We also note that we have a radius 1, and we're centered at the origin. And then we're given the wave equation in terms of v, polar coordinates, yada yada yada. And we also notice that we have full periodicity right here. So this implies to us that we're going to have periodicity conditions down the road. Also note that we're given this initial condition right here, where we have J naught plus J naught, near J naught, blah, 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 blah. And then we have this derivative term. So let's just get started with this problem. So for this Bessel function problem, I'll be delving deeply into each of the steps so that you guys can make sure that you guys understand what I'm doing. For the separation parts, I may skip a few steps here and there, but hopefully everything I do makes sense as we go along. Okay. So starting off, let's draw a shape just to make sure that we know what we're doing. So we have a circle, radius 1. We know we have periodicity conditions, and we know that at the edge of the circle, so this condition right here, which should be in V, I guess, V1 theta t is equal to 0. And then we have two initial conditions that I was talking about earlier, and then we have Laplacian V equals, so actually not Laplacian, del squared V is equal to VTT, wave equation sort of thing. Okay, cool. So let's separate variables. So given this PDE, let's call VXYT a separation of, let's do phi XY with H of T. So such that we separate out these variables, we get phi is equal to 1 over HTT. So now we have all variables on one side and all the variables on the other side. So now we have to decide the value of the separation constant. So remember that in this problem, we want oscillatory solutions because we have a wave equation. We have an oscillating membrane. So therefore, we're going to choose negative lambda. And the reason why I choose negative lambda is to satisfy the relationship on the right-hand side of the equation, where in time, our solutions oscillate. Cool. So moving on, we have to continue separating out this relationship right here. So let's redefine phi of xy equal to f of x. And then I just realized I was doing x and y. Let's change this up real quick. So r theta, oops, r theta, f of r, g of theta. All right, everything should be fine and dandy now, hopefully. Let's take a quick look. Yes, we're good. Okay, sorry about that. So now we'll continue separating variables. We're going to plug everything into the original Laplacian, right? So let's take a look at what we're defined here as our Laplacian. So I'm basically looking at everything here, and let's just plug everything in for phi first. So we have 1 over r ddr of, r phi dr plus 1 over r squared partial theta squared. And this is all equal to negative lambda phi. So plugging in the definition for f and g, so the definition for phi, into this equation, we find 1 over r phi r of f dot g plus 1 over r squared phi theta squared fg is equal to negative lambda fg. So what I'm going to do now is I'm going to divide both sides by fg. And the reason for this is we're going to eliminate everything on the right hand side such that we're just left with negative lambda. And then we can isolate all the terms that have no dependency on the variables. So on this, we're going to get rid of the f term because it's a function of r, such that we're only left with derivative operators on theta. And then we have 1 over g plus 1 over r, 1 over f, r df, because g is not a function of r, so we can essentially just factor that out. So what I'm going to do is I'm going to move, before I move this, I'm going to multiply both sides by r squared now. And the reason why I'm doing this is because I'm trying to isolate this theta dependency onto the right hand side of this equation. So by multiplying by r squared, what I'm left with is r partial r df dr. Let's change these into derivative operators rather than del partial operators. Plus d squared dg d theta squared 1 over g is equal to negative lambda r squared. So I'm going to highlight all the terms that are dependent on r, light orange, and all the terms that are dependent on theta with light blue. So now we notice that what we need to do is we're going to move all the r dependent terms to one side of the equation, so I'm going to move it to the left hand side, plus lambda r squared. Now I'm going to move all the theta dependent terms to the right hand side of the equation. Great. So now what we choose so now we have to obviously choose our separation constant, right? So we have all r dependent terms on the left hand side and all the theta dependent terms on the right hand side. So the logic in choosing our separation constant now is we want to obtain solutions such that we have sine and cosine in the theta direction, because remember that we have periodicity conditions, and those conditions are satisfied via sine and cosine solutions, right? So let's choose our separation constant to be mu now instead of lambda, because this is an entirely different set of separation equations, such that when we solve out the equation on the right hand side, we'll get a solution for g of theta as a linear combination of sine and cosines, but we'll do that later. Okay, so this leaves us with 3 differential equations to solve, which I'm going to circle in dark green. Right, so this leaves us with this differential equation, leaves us with this differential equation in r, and then we also have this differential equation in time. So now the next step in this journey essentially is to solve the diffie-q's. Remember, the rule of thumb is to solve for the eigenvalues that you can solve for first. So solve for the problems where you can find the values of the eigenvalues first. In that case is G, where we have periodicity conditions. So in G of theta, recall that our differential equation is G theta theta is equal to negative mu G. And given periodicity conditions from the table, periodicity bound conditions, our general solution for G of theta is equal to C1 sine m theta plus C2 cosine m theta, where mu is equal to m squared, where m can start from 0, 1, 2. Great. So this is something important that we should probably keep down the road. But note that mu starts from 0, so we have to consider the lambda equals 0 case down the road. So now let's solve for f of r, because that'll help us hopefully solve for the values of the eigenvalues lambda. So in r, we have this differential equation, which I'm just going to copy over on the left-hand side. And this is all equal to mu as well. So I'm going to move mu to the left-hand side of this equation. So just copy and paste everything again. Minus mu is equal to 0. Then I'm going to multiply both sides by f, such that we have r dr, r df dr, plus lambda r squared minus mu times f is equal to 0. Great. So now let's be very careful and cautious and take a look at the two cases of this equation. So let's first take a look at the case where mu is greater than 0, because we know that mu can take two different values, right? So let's leave ourselves a note. Mu is either greater than 0 or mu equals 0. So these are the two cases that we have to essentially have to check. So for the case where mu is greater than 0, we're left with the differential equation that I literally just wrote up here, so we're just going to copy it down here. So what I'm going to do is I'm going to expand this left-hand side, so this left term. So if we do chain rule and then expand it out, what we should end up with is r squared df squared dr squared plus r df dr plus lambda r squared minus mu f equals 0. So one thing I'm going to note here is that you cannot solve this via Cauchy-Euler methods, okay? The reason for this is if we look at each of these terms attached to the differential operators, note that we have an r squared term attached to a essentially like non-derivative thing here, right? So that's clearly just not Cauchy-Euler. In the case that you have Cauchy-Euler solutions, then you will not have to solve for Bessel's differential equation. The reason why we're trying to put this specific equation to Bessel's differential equation form is because we can't solve it using the normal differential equation techniques that we know. So that's the motivation. I'll just write that down. We are trying to get this diff EQ into a form where we know the solutions. Right. So this kind of motivates us in doing the change of basis of z is equal to square root lambda r. And the reason for essentially doing this is we're trying to change our differential equation into a form where we know the solutions. So this change of basis, if you just do change of derivative operators and variables, lands you with z df dz plus z squared minus mu f is equal to 0. And we know that mu is equal to m squared from earlier. So what I'm about to box in purple is what we call Bessel's differential equation of order m. So what I mean by order m is we're essentially looking at this term right here. So the convenient thing about Bessel's differential equation is that for any value of m, where m is equal to 0, m is equal to 1, 2, 3, we can essentially put it all into a solution in terms of j and y. So what I've just said, it might sound a little bit confusing, but hopefully I can clear it up in a moment. So what I'm trying to say here is the solution to the Bessel's differential equation is equal to z c3 jm z plus c4 ymz, where this m is the same m from earlier, okay? I'm going to have to add a new page. Let's do that real quick. Great. So this m can be m equals 0 or m greater than 0. So remember from earlier how we were worried about casing for mu greater than 0 and mu equals 0? Noticing that m equals 0 is fine for this Bessel function makes it such that we only have to test essentially the lambda greater than 0 case for this specific problem, for this specific type of casing incident. So conveniently m equals 0 is satisfied, or therefore. Great, so we don't need a case for m equals 0, saves us a little bit of time. Okay, so now in this type of problem, we have to make a smart and educated guess about which of these terms to eliminate. Which term can we eliminate? So on your exam, you had an annulus problem, and your annulus did not contain the center of the circle. Whereas in this problem, you do contain the center of the circle. Center. I remember the center of the circle has to do something with the singularity condition in polar coordinates. So therefore, we have singularity / boundedness condition, as I like to call it. And remember that this states that the limit of let's do u of r theta t as r approaches 0 must be less than infinity. No, less than infinity. Okay, so let's not forget this boundary condition. So just to quickly review what the graphs of j and y look like. So j sort of looks like this thing. So let's call it, let's say that's J0, and then J1, clearly not to draw on the scale, and then let's draw Y0. So amongst this garbled color mess, hopefully you guys can tell what I'm about to say. So the key things to notice are that J is bounded at x equals 0. Y is not bounded at x equals 0. So these are the key, right? So the key note to take away is that y explodes as x approaches 0. So what this means, right, is that if we think about this in terms of like a circle problem and how we eliminated the natural log term or the r to the negative n term, we're going to get rid of the y term here. And this is because as y approaches 0, y essentially goes to infinity. So therefore, we get rid of this term. And this is to satisfy a boundedness condition. Great. So this means that we're only left with j, and that makes our lives kind of easy. So f of z is equal to c3 jm of z. So now let's evaluate the boundary condition that we were given a long time ago. Let's go all the way back up here to find it. So the original boundary condition we're told is at r, so v of 1 theta t is equal to 0. And that's going to be the key to finding our eigenvalues. So let's do a change of basics back from where we define z is equal to square root lambda r. Now we get c3jm square root lambda r. Remember that f of 1 is equal to 0 is equal to c3jm square root lambda. And if we remember how we define the zeros of the Bessel function, so I'll redraw it real quick over here. So if we start with, let's say, J0 again. So this is J0. The zeros of the Bessel function can be marked every single place here. So alpha 1, alpha 2, alpha 3, alpha 4. So when I say alpha, I mean alpha n is the nth zero of the Bessel function. So remember that when we're trying to find the zeros of the sine function, for example, they're evenly spaced by, evenly periodic by some spacing n pi. Whereas for the Bessel function, these are clearly not evenly spaced. Like if I draw some quick arbitrary rulers here, we can tell that this second zero is longer than the first one. That may not necessarily be the case, but in my drawing it is. And like these two zeros are clearly very close to each other. They also kind of look like faces. But anyways, so therefore we're trying to find the zeros of this Bessel function right here. So zeros. So what we can do is similar to how we define the zeros of sine, we can define the inside of the Bessel function square root lambda to be equal to the iterator for the zeros of the function. In this case, the Bessel function. In this case, alpha nm. Oh, sorry, let's add m here of the Bessel of the mth Bessel function, because the zeros of every Bessel function of order 1 to 0 are different from each other. So if I also draw like let's draw J1 for example. Notice that the zeros of J1, which I'm going to color in with green dots, are entirely different. So I would call this alpha 1 1, where this is J1, and this 0 would correspond to alpha 1 2, alpha 1 3. And then my original ones would correspond to alpha 1 0, 2 0, 3 0, 4 0. Because let's quickly go over this again. So I'm basically denoting the zeros of the Bessel function as alpha nm, where alpha nm is the nth zero of the mth order Bessel function. So this means that my lambda has a double dependence on nm, and that's equal to alpha nm squared, where n is equal to 1, 2, 3 to infinity. Great. So this is very useful for down the road. Cool. So now let's add another page. Actually, let me delete this question because it's an ugly question. Okay. Right, so now we've solved for f of r, we've solved for g of theta, so now we should solve for h of t. H of t should probably be the easiest. So let's just go quickly back up to find out what h of t actually was. Here. And note that we already know the values of lambda. So lambda is always going to be greater than 0 in this problem, right? Because the zeros of the Bessel function aren't going to be 0 necessarily. So drawing this out, the solutions here, h of t are going to be c5 sine square root lambda t plus c6 cosine square root lambda t. Great. Let's check if we have any boundary conditions that can eliminate any of the time dependency terms as our initial conditions, and we do in fact. So if we take the derivative of our time function and set it equal to 0, we can essentially get rid of one of the terms. So let's quickly do that. So in taking the derivative of this thing, h prime of t is equal to c5 square root lambda cosine minus c6 square root lambda sine square root lambda t, and then h0 is equal to 0, and this tells us that the c5 is going to be equal to 0. So therefore, let's get rid of this green box right here before we confuse anybody. Therefore, since c5 is equal to 0, our time function is going to be c6 cosine square root lambda t. Great. So now we have our time dependency function. We have our f of r's, and then we also have our g of thetas, which are somewhere up here. Yes, okay. So let's quickly take a look at the original problem and start to take a look at what we need to deal with now. So now we've solved for each individual differential equation. We can put everything back together and then start solving for the coefficients of this function. It's going all the way back down. So step 3, put together into general solution. So we have let's call it v r theta t is equal to 5 of r theta h of t, which is equal to f of r g theta h of t. Great. So putting everything together, we have v of r theta t is equal to the double sum from n is equal to 1 to infinity, and then m equals 0 to infinity of a n m j m alpha and m r. Oh, I should write a lot smaller so we can write this all in one line. Okay. Alpha and m r times g of theta. Let's do sine m theta times cosine of alpha nmt plus, let's do it on the second line so we don't make anything messy, plus b and m jm square root and mr times cosine m theta times cosine alpha nmt. Right, so I'll quickly annotate everything so it's nice and clear. So this corresponds to f of r, this corresponds to g of theta, and this corresponds to h of time. Same sort of thing down here, f of r, g theta, h of time. Great. So the question that may arise now is, why am I consolidating everything into two summations and not taking a look at the specific lambda equals 0 case for m equals 0? The reason for this is, if we take a look at m equals 0 case, so when m is equal to 0, we don't have any non-constant eigenfunctions, is what I'm trying to say. In other problems, like for example the wave equation, damp wave equation for example, when we have a lambda equals 0 case, we have a linear function and an exponential function up here, and we need to take care of those very explicitly and very carefully. Whereas here, if we take a look at the m equals 0 case, so let's isolate that m equals 0 case here, so a n 0, j 0, alpha's n 0, r times, so we're going to have the bn term because the an term goes to 0, bn 0 cosine 0 times cosine alpha n 0t. This would be the corresponding to the case of when m is equal to 0. And then n is arbitrary. So what this basically tells me here, and what you guys can hopefully tell, is that if we compared this to all the eigenfunctions that we determined earlier for the m equals 0 case, it's the same exact thing. So we're able to consolidate into the summation because the eigenfunctions are either constant or suffice into the summation form. However, if the lambda equals 0 case was a little bit different, like the problem that we'll see later down the road in this recitation, then we have to take much more explicit care of it. But if it's easier for you to be more, I don't know how to say this, if you want to isolate the lambda equals 0 case in all kit problems, and go for it, be my guest. But sometimes if you're able to notice these things, then that's also good. So do whatever floats your boat, essentially. Cool. So now we have put everything together. So now let's solve for the coefficients. Solve for coefficients. So let me scroll back up here because we're given a very long initial condition, and while you guys are looking at this, I'm gonna pull it up and then look it on my computer, so that what we're gonna do is we're gonna essentially copy down this initial condition down below and then find out what the values of the coefficients are. Cool. So go back down here. We have this initial condition f of r theta 0 is equal to j naught alpha 1r plus 1/4 j naught alpha 2r plus 1/9 j naught alpha mr. And then we're going to equate this to the general form that we just saw above. So let's put everything on that right hand side over there. So notice that t time is equal to 0. So therefore we're just going to get rid of the cosine time dependent terms, and then we're just going to bring everything else down. So we have that double sum from earlier. I'm dropping the cosine term because it doesn't really matter here. I'm going to make these a little bit smaller so we can fit everything. Plus everything here. Plus b and n, blah, 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 blah. But the cosine term just goes to 1, so we don't really need to worry about it. Oh god, that's very small. That's okay. Okay, so we have this long garbled mess. Looks pretty bad to deal with. Until we notice that on the left-hand side, notice that all of our all of our Bessel functions. So what I'm going to highlight now, all of our Bessel functions are order m, are order 0, are order m equals 0. So this means that the only solutions that can survive on the right-hand side of this thing, so the right-hand side of this equality, are for the case where m is equal to 0. So that means every single other m term for m1, 2, 3, 4 to infinity have to all be equal to 0. And this is just a simple consequence of equality, right? So j1 can't be equal to j0. So the only term that survives on the right-hand side is for m equals 0. So this simplifies things a little bit. So now we're only left with one summation. But we know that m is equal to 0. M equal to 0 is the only term that essentially survives this entire process. And then conveniently, what we hopefully notice now is that because m is equal to 0, that means the sign terms, so the an0 terms, must also all be equal to 0. b0, j0, alpha n0r, cosine of 0 theta. Right, so the cosine term goes to 1, and this term goes to 0, such that everything else here goes to 0. And if we continue simplifying, all we're left with now is this one summation b. I'm just going to copy this over so I don't have to write it all over again. Now we're just left with these two little terms right here, and this makes life a lot easier to figure out. And that's all that simplification resulted from the fact that we noticed that m had to be equal to 0. Oh, this should be 3, sorry. Great. So now, if we continue comparing, and then we think about this in terms of orthogonality principle, the only terms where we have matching numbers, right? So if we quickly expand the summation on the right-hand side, just to make it somewhat explicit, let's do b10, so the first 0, a10r, and let's do the second one, b20, let's do commas just to differentiate a little bit better, j0 of alpha 20r plus b30, you'll see why I'm doing this in a moment, sorry if it's like tedious, r plus the summation from n equals 4 to infinity of everything else. So all I did was I essentially just plucked out those 4 terms right there. Those 3 terms right there. What you guys hopefully notice now is that these 3 terms correspond to the case where n is equal to 0, right? So n is equal to 0 here. I'm going to highlight this in yellow. I'm going to highlight this one in light blue. So this corresponds here. And then this corresponds here. So this makes our lives nice and easy, right? Because the only relationships that satisfy these properties are when the corresponding Bessel functions are equal to each other, essentially. So what we hopefully notice now is that for the yellow highlighted to be true, b10 must be equal to 1, right? Don't overthink this. It's popping out right at you. For the light blue one, for these two relationships to be equal, b20 has to be equal to 1/4. And then for this orange one, for this relationship to be true, b30 has to be equal to 1/9. Great, so that makes our lives nice and easy. And therefore bn0 for all n greater than or equal to 4 have to be equal to 0, because that doesn't satisfy our relationship that we found in the initial condition. Great, so this means that we know everything, right? So this corresponds to the cases where m is equal to 0, and then this is n equals 1, n equals 2, and then this is n equals 3. Great, so let's put everything to a final solution now. So now this solution becomes a lot more simplified because we know that all the an zeros must be equal to 0, otherwise we won't satisfy our initial condition. So in the final step of this problem, we isolated the specific cases for m is equal to 0 and then n is equal to 0. So if we take a look at our general solution, which I'm going to bring down here real quick so we can reference it while we're copying down our answer, we know that we have 3 terms, n equals 1, n equals 2, and then n equals 3, and all 3 of those correspond to m equals 0. So therefore, our final solution is going to be j0, alpha 1, 0, r, and then we know that cosine 0, so that we can just move on with our lives there. But we also have that time dependency term, so we cannot forget that. 10t plus 1/4 j0 alpha 20r cosine alpha 20t, and then the last term, which is 1/9 plus 1/9 J0 alpha 30 T, R times cosine alpha 30 T. And this is our final solution to the problem, VR theta T. And this is the first example we're going to do. So this is more of a slightly more difficult Bessel function question, I would say, mainly because the application of the initial condition can be a little awkward. But hopefully this clears up any confusion in regards to standard Bessel function questions. So just a quick overview of what we did. We were approached with this problem with a nasty initial condition. So we drew the shape to sort of figure out what was going on there. We separated the variables and then justified that we have two different separation constants. And then we knew that we had to solve these differential equations, and we chose to solve the g of theta differential equation first because that would give us solutions to eigenvalues more quickly, specifically mu is equal to m squared. Then we solved for f of r, and we noticed that f of r is specifically in the form of the Bessel's differential equation. And the solution to Bessel's differential equation of order m is a linear combination of jm and ym. We eliminated the ym term to satisfy the boundedness condition. And then we found the zeros of the Jm Bessel function by noting each of the zeros by alpha and m, where alpha and m is the nth zero of the mth order Bessel function. Then we solve for the time differential equation, and then we put everything back together. After putting everything back together, we solve for the coefficients by coefficient matching essentially, and then we put everything together into a final solution. Great. So hopefully that clears up any sort of confusion about Bessel functions in this first example. So what I'm going to start off with is sort of talking about the basics of Laplace equation on a circular cylinder, because the cylinder problems is when we start to see modified Bessel equations. And then what I'll do is I'm going to give you guys a specific link to the Laplace equation on cylinder and then modified Laplace equation, so that we can sort of take a look. So you guys can sort of take a look and get an idea of like those sort of problems. So I think for the rest of this recitation, what I'll do is I'll mainly focus on sort of like basic ideas you should take away from Laplace equation in a cylinder, and like sort of the basic understanding of what you need to have in order to do these problems. So this is in your textbook, chapter 7.9.1, Laplace equation on cylinder, okay. So what I'm going to sort of break down is a very light overview of like what you guys are looking for, because I think it's not too different from what you guys have seen. It's just a cylinder, so it can be a little bit like different just by the words, but you'll see exactly what I'm saying, right? So what we're going to do is we have Laplace's equation on a cylinder, so big old cylinder boy right here, and then Laplace equals 0. So we want to write this out in terms of an expanded form, in terms of cylindrical coordinates. And the reason for this is we're in 3 dimensions as opposed to 2 like before. So the equation I'm writing right now, so r squared includes this extra du squared dz squared term right here. So everything on this left hand side is for that covers r theta, so that can be that r theta basically covers a circle, and then this z term covers cylinder, so the sort of in the direction of the z term. So if we draw a quick like x and y coordinate axis here, r is essentially the vector that goes there, theta covers this theta, and then z is everything in this direction right here, so in the vertical direction. So r theta z coordinates, so cylindrical coordinates. Hopefully you guys have seen this before, and hopefully you guys can sort of visualize like what I'm trying to say right here. So the problem in the book gives us a cylinder. Let's make this dotted, where we have 3 sides with 3 different boundary conditions. So u is equal to beta r theta. The lateral side of the cylinder has a initial condition u equals gamma theta z, and then the bottom of the cylinder has u equal alpha r theta. So in order to solve this problem, we have to split it up into its appropriate parts. Remember that we can only solve these problems if one of the sides is non-homogeneous, right? Because if any two of the sides were non-homogeneous, we would not have enough information to be able to solve for the eigenvalues. So I'm going to break this up into v equals 0, 0 everywhere else, plus top is 0. Let's call this w. Let's make the bottom of w be equal to alpha r theta, so the non-homogeneous one, and then the side of w be equal to 0. And then let's make the last one, let's call it gamma or something. So, oh wait, our condition is gamma. Let's call this, I don't know, let's call this z. No, that's probably not good either. Let's call it q, why not? So top of q is equal to 0, bottom of q is equal to 0, but then the lateral side of q is equal to gamma theta z equals q. So now each individual solutions of these cylinders will garner us a solution such that we can take the linear combination of all three, add them together, and that's a solution to our original PDE. So how do you approach these sort of like complex three-dimensional problems? You would approach these cylinder problems the same exact way as you would before, with separation variables, right? So don't get bogged up by the fact that there's like a bunch of variables going on. Just approach it the same way as you would before. So remember that we want to separate variables. So let's call u of r theta z. Actually, to sort of keep with the notation, what I'm doing here, so in order to make this like a solvable problem, so this is v. Let's solve for v. Here, so remember separating variables. Let's first define the separation of u r theta times h of z, such that we get 1 over r phi 1 over phi plus 1 over r squared 1 over phi v theta squared is equal to negative 1 over h squared v h z squared. So let's take a look at our cylinder for v and make a logical conclusion about which separation constant we want. So noticing that the top is non-zero, so the top is non-homogeneous. Top is non-homogeneous. And then the bottom is 0. So what this is essentially, this type of cylinder problem that we're doing in V, so let's take a note here, in V, we are solving a cylinder with non-homogeneous top and homogeneous lateral side. So let's say the height of our cylinder is h. So for V, for cylinder V, this is saying that V of r theta h is equal to whatever the non-homogeneous thing is, beta r theta. This is also telling us that at the bottom of that cylinder, we're equal to 0. And then this is also saying that for the radius of the cylinder, which I'm going to denote by big R, so at the outer edge of that cylinder, for any height, we're equal to 0. So let's quickly translate like what I just said there to the cylinder, which is literally the one I drew above. So this boundary condition right here correlates to this one. This boundary condition right here correlates to the bottom, and then this boundary condition correlates to the lateral side of the cylinder. So in starting this problem, we're going to choose the separation constant to actually be positive now. And the reason for this is because we have non-homogeneous boundary conditions in Z, in the Z direction. And seeing that we have non-homogeneous boundary conditions in Z, we're going to want exponential solutions. And the way to get exponential solutions is to make this equation satisfy that condition. So in order to satisfy the exponential solutions case, we need to make sure that this lambda is equal to a negative number. Sorry if that was unclear, because Now, we can clearly see that this relationship, HZZ is equal to lambda h, and that will generate just sinh and cosh solutions, which we can then use to satisfy the fact that we have exponential solutions in the z direction. Otherwise, the separation basically remains, if not pretty much exactly the same as before. We're just going to continue separating the variables, continue chugging along with how we did it in the previous problem. So what I'm going to link in the bottom of this video is links to Laplace on cylinder, so for a basic Laplace on cylinder problem, and then modified Bessel functions, which is more of an advanced topic, which I'll cover in more detail in the future recitation. Modified Bessel functions, Laplace on cylinder again. So yeah, these two links will be in the description below, and yeah, I hope this video helped you guys out. So the main focus of this video is to mainly catch everybody up on Bessel functions, and then cover a little bit about Laplace equation on cylinder, cover very minimal basics, and hopefully Eduardo can cover most of the rest of the sort of theory and ideas behind Laplace in a cylinder. So sort of what Laplace and cylinder questions can actually model is like sort of, if you can imagine this is like, I don't know, radioactive nuclear power plant or something. We're trying to model like the radiation flow inside that plant. I don't know, dude. Or the heat flow inside a can that you heated up in the microwave for some reason. Yeah, the whole idea behind these is modeling heat flow or how wave equation oscillates, or some sort of modeling of a real life phenomena. But yeah, hopefully this helped. I would highly recommend you guys watch those two videos below. But anyways, have a good day. Thanks for watching.